Okay, we'll talk about typical test equipment. So one of the most common pieces of test equipment that you're likely to have is called a voltmeter, or essentially a multimeter. This is kind of old style analog. This used to be kind of the gold standard, these Simpson meters. You can still buy them. Um, there's usually a guy that shows up at the Melbourne Ham Fest with a bunch of older ones selling for about $300 a piece. Um, it's an analog device. It has a low input impedance, which is one of the things that's uh, one of the cons, because it tends to load the circuit that you're trying to measure.
Mm.
So it can affect the measurement depending on what it is you're measuring. Now, if you're measuring, your 120 volt AC outlet, it's not going to affect that reading. But if you were measuring uh, a very low level signal in a radio, it might affect it to the point where you don't even see the reading. It could almost seem like it's shorting it out. Uh,
So that's
it's
not your preferred. That wouldn't be a
well,
preferred choice.
it it depends on what you're doing. Um, it's not as accurate as a digital meter, which we'll talk about in a minute.
Hmm.
Uh, its one advantage is because of that analog needle, you can see changing values. So if you're looking at some signal and saying you're trying to adjust something, you can see the needle move as you adjust it, like you're tuning in a circuit or something. You can't normally do that on the digital meter because you'll just see what if it's varying fast, you'll just see like 8888. This is a modern version of the Simpson. This is a digital one. It also costs about $300. It says low cost, and you can get very cheap ones. If you go to Harbor Freight, you get them for a simple one, like 4 function, for free. But you can get them for 5, 10, $20 that are lots of modes. Most of the stuff that this one does, you can get for in that range. They tend to have a very high input impedance, so there's very little loading on the circuit. And they're usually fairly good accuracy, much more accurate than trying to read where that needle is on the analog meter.
But I noticed you said high input impedance.
Yes.
So that's going to mess up your reading a little bit, correct?
No, it's going to have less load.
Okay, okay.
In other words, your analog meter is going to be like putting a low value resistor across what you're measuring. So it's going to
Change it
uh,
a little bit.
uh, kind of suck up part of the current.
Right.
Whereas the um, digital meter is going to be in the megohm range. So it's going to have very little effect. It's going to, uh,
No, it won't draw off of it.
right.
Right.
It'll be in like microamps instead of milliamps. Okay, the next one that you may be come familiar with, you may or may not have, is an oscilloscope. If you do any kind of building or working on radios, you probably need an oscilloscope. Uh, just general stuff, you probably need a multimeter like we showed. An oscilloscope is a device that shows, uh, can display waveforms in the time domain. So you put a signal into one of the vertical channels, and you can have an oscilloscope that has 1, 2, 4, uh, unusual, but maybe 8 vertical channels. So you can look at different signals at the same time. And the amplitudes will be displayed vertically on the screen. The horizontal part of the screen is displaying time. So you'll have a time-based control, where you can vary uh, how much time is being displayed across the screen. So when you look at the amplitude versus time, you'll see this envelope of the waveform. There's also usually a triggering input. You'll have the option of doing some form of internal trigger where it can detect when the signal, say, crosses a certain value or crosses 0, and start displaying the trace, or select some external input device where you can control at what point in time you want it to start displaying the trace. This is used to be a fairly common, fairly high-end kind of workbench oscilloscope. Tektronix was probably the most popular back in the day. And you'll see this sine waveform where we're displaying the amplitude of this signal versus time. And I can't quite read it. See, it's set to, looks like point, well, maybe that's 2 milliseconds per division time-wise across here. So you can figure out what the frequency is. Some of the fancier ones would, and that may be what this is displaying. The more modern ones will, and I think I have a picture, show you a
Question.
lot more information, but essentially you have one or more input channels, and you can adjust the sensitivity with these knobs and either display one or both or 4. And they just show you amplitude versus time. This is a more modern digital one. And you can see it's doing 4 different waveforms in color. And it'll have a lot of things like utility stuff where it can actually go in and measure the amplitudes at various points, the frequency, amount of phase, all sorts of uh, parameters. They're getting kind of amazing as what they can do.
Question.
Yes.
Okay. I'm embarrassed to ask this. If I'm looking at it vertically and I'm looking for the waveform amplitude, what am
Mm-hmm.
I actually looking at? Amplitude I thought was loss or decrease,
No, amplitude is the value.
the
Like if you're
value.
looking at
That's strength, like
a
the strength.
signal, okay, it would be the voltage, uh,
Okay.
the instantaneous voltage over time.
So
Now,
that
this
would be
top one you're looking at is actually what we call an envelope pattern of, it could be audio, it could be RF, uh, a
and when
modulated waveform.
and I'm going to break this down. I'm so sorry. Voltage. Is that my power? Is that my strength? Is that my
Voltage is the electromotive force called EMF.
okay? But I mean, I'm
It's the
trying to simplify.
force that's trying to create a current through a resistance.
Okay, so it's okay.
And we
So
haven't
basically,
got there yet, so I don't
I
want to
know, but
go
I
into.
mean, I'm just
Okay,
trying to think for myself how to simplify it. It's the power. The current is the power. It's the energy.
the current, I mean, the power is the current times the voltage, the product.
Okay. Okay.
This is just displaying voltage.
Okay.
So it's how the voltage is changing on this waveform versus time.
Nanette or
Yes.
Bob, when we were
Yes.
talking about the power, you remember the circles? Let me turn on my picture so you can see me do this.
Okay.
So, um, back when we were uh, learning about the Ohm's law and all those
Yeah.
things,
Right.
that was when we learned about the difference between current and power and all those, and ohms and impedance and all that. So it's a very specific terminology that Bob's using here, as opposed
Okay.
to what we get along with when we're plugging stuff into the wall. At least that's, and I haven't remembered all that stuff, but that's
That's
what
why
he
I'm
was
trying.
saying.
Yeah. Yeah. Because I have a hard time because I don't have a common something that I can relate to identify that. So I'm trying to like
Yes,
give
and you
myself.
have to go back because it's not something we commonly, I mean,
Okay.
you and I never having done electronics, I'm
Right. Okay.
guessing, we don't have that. We have to study it and remember what the terms apply to.
I
And
got
and I will be going back to my
it. I
wishes
know.
book to
Okay,
Yes.
remember this.
well, let's look at the blue line.
Uh huh.
Okay, on that channel, what we're looking at is just a simple sine wave. So it's a voltage that's varying sinusoidally over time.
Okay.
Okay, and you see it,
Right.
down, up, down. The purple one is um, a definitely a non-sinusoidal. It's kind of a recurring pulse with some ripple.
Mm-hmm.
The blue, or cyan, I guess that is a digital pulse where we're at 0 volts. It jumps up to some voltage, and I can't tell from this what, because there's no grid. Um, and for a period of time, it goes back down.
Mm-hmm.
Could be a clock pulse or something.
Mm-hmm.
The top one is actually an envelope waveform of a modulated wave. And what you're actually seeing, and it would vary depending on how we change the time base. We're looking at it uh, with a slow enough time base that we're seeing the modulation. We're not seeing the carrier. What all this shaded stuff is in here is actually a high frequency carrier and how it's being modulated by some audio signal.
Okay.
And that's one of the purposes of, and I think we even will have a question about looking at the envelope of this RF waveform.
Okay.
Could be the output of your transmitter.
I understand. Okay, that's kind of what I was trying to get to is like how do I take what I'm seeing and put it into something I can relate to as far as, but it's like a wave.
Yeah.
It's your frequency wave.
The one really neat thing I thought about in when I found this picture and looking at it, nothing's hooked up to the inputs yet. It's got displays on the screen, which is magic. Okay, so one of the main applications of using an oscilloscope is to look at your RF envelope pattern. Um, and in this case, you feed your transmitter output. The key here to remember the attenuated RF output. An oscilloscope is not set up to take a 100-watt input. So you have to run it through some sort of attenuation device to get it down to maybe a milliwatt or something so that you can connect it up to your oscilloscope. Would be the same if you were doing it to a spectrum analyzer, which we'll talk about in a little bit. And the horizontal axis is In this case, we had it set to show your modulation frequency, or actually, it was showing a couple cycles, so it was uh, actually like half of what the modulation frequency was time wise. Um, if you're looking at, uh, say, a CW signal, you would see more like a square wave pattern instead of that nice symmetrical up and down sine wave. And you could see how fast your CW pulse rises and falls, which will determine how much key clicking and distortion it can cause. You actually want your CW signal to be kind of rounded on the front edge and on the back edge instead of a nice square wave.
Bob,
Square
could you,
waves have harmonics, and we don't like those. Yes.
so when you talk about that, if you could go back to the previous slide and we can look at the envelope waveform
Mm-hmm.
and it's modulated.
Right.
And at that point, I think, well, what? I mean, I think of waveforms being more like the blue one at the bottom.
Well,
That's a waveform. And then I can follow that this
okay.
purple one is also.
But
And I can even go as far as the cyan one, but this is two.
this is a complex waveform. It's two signals.
Okay, in radio land, do we have these in radio land?
Yes. This is what the output of your transmitter in AM mode would look like. Because actually, this is displaying two sidebands and the carrier.
Thank you.
I
I'm
got
with
you. See,
you.
that's
Yay.
thank you,
Got
thank
it.
you,
Got
thank
it.
you.
Okay.
Now,
If you try to look at a single sideband signal, it's going to look like noise because you have no carrier in between, and you just have kind of the modulation, which is what your voice signal kind of looks like, and it's very hard to sync it up. So it's hard to get a picture of a single sideband unless you put in a constant tone or something.
Well, that's too bad. I didn't, then you lost me again.
Oh,
But
why?
because I don't really know, I mean, I'm like Nanette trying to think of, okay, what's a carrier band? I had this idea of what a carrier band was, a
Okay,
carrier
well,
was.
all right.
Is it, I mean, is
On
it a
this
wave?
waveform, the yellow
Okay.
one, okay,
mhm.
if I was to change the time base to a much shorter period where I could display the carrier waveform, I see some sine wave like the one at the bottom, and
Right.
I would not see the modulation of it because it would have negligible effect on just a couple cycles of the carrier.
When I think of modulation, I think of change, right? Modulation is a kind of change.
Right. When
So
we
there's the
modulate it,
carrier.
we're if we just put out the carrier signal with no modulation,
It'd be a
you'd
straight
just see
line.
a band, okay, of this yellow.
Oh, look at, I have it in my book. It's just a big rectangle all the way across, just a
Right.
solid thing.
Let me go
Yes.
back.
And then modulated, it's on either side of that.
If it was just the carrier, I'd see something, except they'd be parallel,
But
and
it's
it'd be
still a
all sound.
waveform. Yeah, but how is
Well,
it a waveform if it's
but that's just because I'm looking at it at a much slower period of time. So I'm
okay?
seeing so many cycles of the waveform that it just is a blur. As I uh,
Stretch it out in
as I
time.
stretch it out by speeding up the time base, instead of looking at it over a milliseconds, I'm looking at it over microseconds. then I can actually get to where I see the actual waveform of the carrier. But if I do that, I don't see the waveform of the modulation.
So the modulation and is operating on both
Oh,
the upper and the lower part of that
yes,
block
yes,
because of upper sideband and lower sideband, for example.
right.
Okay, I think we should stop there.
No,
Are
that was
you okay?
informative because I mean that's a good visual. And now that we understand it better, it's sinking in.
Oh,
Because to me, I mean, even though we're learning all that stuff, it's still out in space. It's like something I have to try to put some context to because I don't know, I've not experienced looking at it, understanding it, describing it, using it. It's like faith. You just have to know it's there. It's like,
okay. But the key thing to remember on this one is if you want to look at your transmitter output, you need to look at the attenuated output. Otherwise, you'll be buying another oscilloscope.
Oh, right.
Uh, Another useful device is an antenna analyzer. And these have come down since the advent of the nano VNA, which you can get for under $100. And it does the functions of um, VNAs that used to cost tens of thousands of dollars. So it's one of those amazing things. It will measure SWR. So you connect it to the feed line of your uh, antenna at the transmitter end, but not with the transmitter connected. And it actually it sends out a very low level signal about 0 dBm and will look for reflections coming back. So it can determine how much signal it sent to the antenna and how much signal came back from the antenna and display the SWR either as some sort of amplitude versus frequency plot or as Smith chart, which we won't go into because that'll really blow your mind. But Smith charts are great, but we talk about those in the extra. Um, if you have strong signals nearby when you're trying to use one of these devices, it can affect the measurement because some of that signal can be picked up even in the coax that you're using to connect your device to the antenna. So that's one of the things you have to look out for. It can also be used to measure the impedance of a coax cable. Um, so you can terminate it and in what you think is its correct impedance and actually measure it and see whether or not it's really a 50 ohm cable or not. You can also, by either shorting or leaving the other end of the cable open, you can measure how long it is electrically. It won't necessarily, you, you can calculate what the physical length is if you know the velocity factor of the coax cable, which you can look up as part of the specification for that particular cable, which is really a measure of how fast electrical waves travel in a cable versus the speed of light. So when they're traveling in a wire or a coax cable, signals go slower than the speed of light. And that velocity factor is that ratio. Some of these coax cables may have a velocity factor of 0.6, which means it's just a little more than half the speed of light.
Hmm.
You can also do cable loss measurements where you use it as 2-port. You're sending a signal in one end of the cable and you're looking at the output of the cable on the other port of the device and see how much loss in dB there actually is in that cable, plotted versus frequency, because the loss will go up with frequency. That's a future question to remember. There's a typical little nano VNA. There's a bunch of different models of them. They're all about the same. They run around $80 to $100. Most of the newer ones go up to like 3.5 gigahertz. It's an amazing device. It happens to be showing you several displays. The one in the background is that Smith chart I talked about. It turns out this picture is a little distorted because it should be a circle, not an ellipse. This is a more standard antenna analyzer. Happens to be one of the more expensive ones, called a Rig Expert. They have lots of models. This is one of their newer ones. It has the zoom feature, kind of like you were talking about earlier, where you can zoom in on you can kind of spread the display out and zoom in on it. It will do some of the things that the Nano VNA will, but not all of them. It's basically used to show SWR when you're trying to actually tune an antenna by adjusting the length of the elements or adjusting your whatever feed device you have to try to match the impedance of it.
Can I ask
These
you a
are
quick question?
fairly expensive.
So if we are reading that right now,
Uh-huh.
this right here, so it's about 1, and then what's the other side of it?
Yeah, right there.
Yes.
Well, it's showing 0. Well, you can't get 0. The best you can do is 1-to-1.
So I'm guessing that's 1-to-1 because they both
Well, it's
hit the
close
same
to
spot.
it. You'll never get 1-to-1, but yeah, it's close.
That's very close.
And
So
it's actually, I think it's probably on this scale is probably showing you, if you were on the line, it would be 1 to 1.0.
Mm-hmm.
And I'd say we were 1 to 1.1 because it's about halfway between 0.2 and 0.
I just wanted to verify it's the two where they intersect. That's what we're looking at.
Yeah.
Okay. I just wanted to make sure I was reading it correctly.
And its frequency as you go across. So it's centered right now. It's telling you that it's at 140 megahertz, and your bandwidth is plus or minus 250 kilohertz. So this end over here would be 14 or 140 megahertz minus 250 kilohertz, and this one would be 140 plus. So that's the spread that you're looking at.
So when we're talking on the radio, an antenna might be tuned for one type of frequency and not another, which is why we switch antennas, right?
Yes. And also in this case, you see this blue section.
Mm-hmm. Mm-hmm.
That's actually the 2-meter band. So it's showing you that this antenna is resonant outside of the 2-meter band.
Mm-hmm.
When you're actually within band, your SWR is closer to 1.5 up to 2, which isn't
Which is
bad.
still okay. Yeah, that's still okay.
But it's not nearly as good as if we shifted this up.
Right.
Which
and
we could do by shortening the elements on your antenna.
Okay, so making your that's what I was going to ask you. How do you do that? So you'd have to go outside and fiddle with it.
Yeah, you physically have to change the antenna.
Okay.
Okay. Another one is a directional watt meter, which those devices actually have within them, both the Nano VNA and the uh, antenna analyzer rig expert. Um, that one we were looking at is probably about a $300 device. They're actually made in the Ukraine. It's the only place that makes them, and they're still making them. Um, the directional watt meter measures forward and reflected power. Like when we looked at that um, external antenna tuner earlier, they had the display on it with the two needles, where one was showing you forward power and one was showing reflected power. Um, that was because there was it's essentially a directional watt meter. It has what's called a directional coupler, which has two outputs. One would be the reflected and one would be the forward. And they just amplify those signals and display them either on an analog needle or digital display. So if you measure forward power and reflected power, uh, you can actually calculate what the SWR is. Most of these devices do that for you, but the formula to actually calculate it is here. It's not something you have to remember, but it's simply 1 plus the square root of the ratio of forward and reverse, and or reverse over forward, and 1 minus the square root. So it's fairly simple to calculate if you have those two numbers.
Well, we have to know that on the test, that
No,
formula.
the formula, no.
Okay, good.
Um, this is another uh, external watt meter, directional uh, watt meter that again is using the twin needle approach. So you see the two scales, and then the red is uh, wherever, whichever one of these lines the needles cross at the same time would be the calculated SWR.
So
And
this is a
sometimes,
directional.
yeah, it's
This
direction because it's showing you forward and reflected.
so this is a directional watt meter.
Yes,
Okay.
that's also got a calibrated scale for SWR. So it's doing the math of that formula. Somebody calculated that and drew these lines. And what you want, regardless of what your SWR is, you want this number to be as low as possible unreflected. And that usually results in a very low SWR. Some of these will have this peak and average, um, and it'll be a little bit different than the way it does the measurement. Okay. Because sometimes you can get an erratic measurement if you're getting uh, external signals on the line from other interference, like we talked about on an earlier chart. And sometimes they'll have ranges, okay, for different frequency ranges. The other thing you have to be sure of, like a lot of these test instruments, you need to make sure that it operates in the range that you want to use it. Now, see, says 1.8 to 60 megahertz, so it really is only good for HF and 6 meters. You could not use it on VHF or UHF. Sometimes I have one that has a switch and it does both, but you have to either switch it to the VHF UHF mode or to the HF mode. Okay. Uh, one of the things that's routinely done to try to measure how linear your transmitter is, or your power amplifier, is to do what's called a two-tone test. And you use two audio signals. The key is they're not harmonically related. In other words, you wouldn't use 700 and 1400 hertz because 1400 would be the second harmonic. So it's two numbers that don't have any harmonic relationship. It's kind of like trying to use prime numbers. The 700 and the 1900 are kind of the de facto standards that are used, although you can use any pair that you want, as long as they're not harmonically related. So when you feed those in as a modulating signal instead of a voice signal, what you should get out, if you have a perfectly linear system, are those two frequencies at shifted up by whatever your carrier frequency is. If you have any nonlinear products within the amplifier, and you will have a small amount because nothing's perfect, you'll have some intermodulation distortions or other modulation products, which are typically the odd harmonics that show up. And you'll see those lines if you look at it on a spectrum analyzer. So when you do the two-tone test, you want to see anything besides those two frequencies at as a very low level. This is kind of the technical part of what happens is you're feeding these two signals into a summing device, feeding it into your transceiver, and you're looking at that on the signal analyzer, which is like an oscilloscope, except it's different. Remember, oscilloscopes looked at amplitude versus time. A signal analyzer will look at amplitude versus frequency. So it's a frequency domain device as opposed to a time domain device, which is an oscilloscope. So what we're looking down here is kind of like what you might see on a signal analyzer. And we'll see the two F1 and F2 signals that are 700 and 1900 hertz, shifted in frequency by whatever carrier we were transmitting at. And then we see all these other products. Ideally, you want all these to be as low as possible, but you will almost guarantee to see some of them, hopefully down below the 43 dB level. And we call these intermodulation products. And you don't have to remember all these numbers until you do the extra, and then there will be questions about 2 times F2 minus 1 and 2 times F1 minus F2, which is one of the harder ones. This is an actual spectrum analyzer display. These are up, let's see, what is this in 1 gigahertz is where the carrier is. And in this case, we aren't using the 700 and 1900 hertz. We're just doing the amplifier, and they're using two much higher frequencies because this is a UHF amplifier. But you can see these, the carriers down here, and these harmonics are, so what are we looking, 10, 20, 30, 40, 50, 60, 70 dB down. So that's good. Actually, 73 dB down and 74 dB down.
Okay, so I have another question.
Okay.
Again, this is gonna, I'm embarrassed to ask, but when you say carrier,
Hmm.
are we talking about somebody that's utilizing that signal? What is a carrier?
When you transmit uh, a radio wave,
Mm-hmm.
okay, at a particular frequency, we call that the
Mm-hmm.
carrier frequency.
Okay, that's what I was wondering. Okay,
Okay, it's called a carrier because it's used to carry the information.
I understand.
The carrier itself has no information. It's
Okay,
like we showed, you just would see that bar. It's a
right.
constant amplitude. So the information is the modulation or changing the amplitude of the carrier. So that's how it carries the information.
Okay. So basically, the carrier is the person initiating the thing and how it generates out. That's the carrier?
That's the signal. Yes.
Yeah, okay.
It's
I just,
not, it's not a person. It's
no,
not a
no.
person.
Well,
Right.
it's,
It's, if
but
you,
it's,
if supposing you, this is another analogy, and it is obviously an analogy, not the real thing, but imagine I could make two voices at once.
Okay.
And I go, ah, and
mhm,
that's the carrier frequency. And now I could make on top of that second tone,
mhm, mhm.
and they go out together like a bit of harmony.
Okay,
That's a
So
two-tone test.
so
okay.
the carrier is the drone signal, so to speak.
Right.
Uh,
I
and
understand.
got it. All right.
Okay.
I
Is
just
that
wanted to
not a
make sure
bad
that,
analogy, Bob? Is that okay? That one?
Yeah. Now
Okay.
remember, we're talking amplitude modulation
mhm.
for now. Now, what's going to bend your mind a little bit when we talk about single sideband, which is still amplitude modulation, we suppress the carrier. So the information is now only contained in the sidebands, either the upper or the lower, which is why I said it's very hard to look at on the oscilloscope because you have no carrier there.
It's a gap.
Yeah, the carrier is there inside the radio when you're
Mhm,
generating the signal,
mhm.
but you get
Ooh.
rid of it before you actually transmit it. So you only transmit the sideband that's shifted in frequency up to where either the above or below the carrier frequency. But there's no carrier there, or there a very small amount of carrier.
So no drone,
No,
just the
no
tones.
drone. That's what makes single sideband more efficient because all your energy is just in that sideband.
This was so good.
Well,
Okay,
I'm getting blown away, but I understand. This is new to me, so I'm trying to suck it all in.
Okay, well, just another, we only talked about AM and single sideband and
Hmm.
CW, which is AM, you're turning the carrier on and off. And there, the carrier is there when you're doing a did or a da.
Hmm.
So the information is carried in the carrier being on or off.
Okay, I think I understand.
The other mode is frequency modulation.
Hmm.
The carrier is there at a constant frequency, and we modulate the carrier by changing the frequency, not the amplitude. So
cool.
an FM signal will still look like that horizontal bar, but if you start expanding it, you'll see that the actual carrier itself changes frequency. Your sine wave will get closer and together and farther apart on the peaks as you vary the frequency.
Okay.
So in all cases, the carrier is called that because that's what is used to carry the information, even if you get rid of it after, when you transmit. Okay, first question. What item of test equipment contains horizontal and vertical channel amplifiers?
That would be
Delta.
alpha. Oh, the delta. Oh, yes, yes. Sorry, wrong one. Yes.
Right. Which of the following is an advantage of an oscilloscope versus a digital voltmeter?
Charlie?
Mm,
Delta.
Delta. Yeah.
Right. You can
Oh,
look at a
that's
complex
right.
waveform. If
Yeah.
you sent that top waveform, we looked at to a looked at it with a digital voltmeter.
Hmm.
Can see.
Um,
Yeah, not precision. That's right.
Useless.
Not
Useless.
sure what you'd see.
Yeah.
A
I mean, it
snapshot. You do see
it
the
would move
snapshot.
it might move the needle, but it wouldn't tell you anything useful.
Hmm.
Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter?
Delta.
Alpha.
Alpha.
Is it alpha?
Yep,
The keying waveform.
right. The little
Oh,
square.
that's right. It was the blue. Yeah. Okay. Yeah. 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 Yeah.
What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal?
You kept repeating that attenuated RF output. Yeah, you kept saying that over again. So delta
Right.
Delta.
Like I said, you'll only do the unattenuated once.
once. Yeah.
Why do voltmeters have high input impedance? They should say, why do some?
Delta.
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 Mhm.
All right.
What's an advantage of a digital voltmeter as compared to an analog voltmeter?
Charlie.
Charlie. Yeah.
What signals are used to conduct a two-tone test?
Non-harmonic. Baker.
Beta. Beta.
Bravo.
Bravo. Bravo. I always want to say beta. I have to think about it. Bravo. Yes.
Yeah, Baker. I got to quit doing that.
What transmitter performance parameter does a two-tone test analyze?
Transmitter.
Alpha.
Alpha.
Alpha linearity. Yeah.
When is an analog multimeter preferred to a digital multimeter?
Bravo.
Delta.
I say bravo. Oh, analog. An analog.
Analog versus digital.
Or I was going the other way around. Okay, analog. Oh yeah. Yes, delta. Because you can tune it better.
Which of the following can be determined with a directional wattmeter?
SW. Alpha. SWR.
Which of the following must be connected to an antenna analyzer when it's being used for SWR measurements?
Charlie.
You have to have the feed line and yeah, Charlie.
Charlie.
Of course, that assumes that you're trying to measure the SWR on your antenna.
Yeah.
You could measure something else. What effect can strong signals from nearby transmitters have on an antenna analyzer?
You get some
Uh,
bad interference with the readings. So
Bravo.
Charlie.
Bravo.
Bravo.
Oh, bravo.
Because it can be, even though coax are shielded, they don't prevent all signals from getting in. Depends on how strong it is and the frequency. So you can pick up some interfering signals even on a shielded coax. Which of the following can be measured with an antenna analyzer?
impedance. So Charlie.
Right.
Alpha. Oh, shoot.
No, you need a signal strength meter to measure the front to back ratio. All right.
Stop your recording.